Today is a special project because, for the first time, someone trusted us with a car like this. As the car rolled into the workshop, everyone stopped to admire it. And honestly, just look at it. A beautiful classic design, timeless curves, and details that make you wonder if anything should even be changed. But this car is not here for a normal restoration. It is about to go through a completely different transformation. And the question is, do you know what car this is? Because what happens next might surprise you. To begin transforming this classic MGA into a fully electric machine, the first step is also the hardest, removing all the old components that are worn out and no longer usable. Starting from the rear of the car, I removed old wiring, deteriorated rubber hoses, and damaged components that had been sitting untouched for years, clearing space for the new electrical system. Next, the old front battery system was carefully removed from the car, revealing an empty chassis covered in dust and rust, marking the beginning of this transformation. Before the new electric motor could be installed, I had to deal with one important part that is often overlooked: the old metal mounting brackets that had developed rust after years of use. Each bracket was removed from the car and carefully inspected before being cut, ground down, cleaned of rust, and reworked to restore surfaces that had deteriorated over time. With the fabrication completed, all mounting brackets were coated in black paint to protect the surface, reduce rust formation, and improve long-term durability inside the engine bay. Once the paint had fully dried, the brackets were reinstalled, aligned, tightened, and securely mounted back onto the chassis in preparation for installing the new electric motor. These may seem like small details, but steps like these often determine whether the project will remain reliable for years to come. Next came the disassembly and restoration of the battery pack, one of the most important parts of the entire system. As the black protective cover was removed, the large battery modules, fuse system, relays, and internal bus bars were finally revealed. The battery modules were inspected directly inside the tray, checking connection points, wiring, and supporting components before starting the full restoration process of the battery pack. I then worked on the battery tray by tightening all mounting points, cleaning threads, reinforcing bracket positions, and ensuring the entire structure was solid before reassembly. Once the mechanical work was completed, the focus shifted to the BMS system, reconnecting cell tap wires, checking individual cell voltages, and correcting connector alignment to ensure proper system operation. Finally, cables, sensors, and mounting brackets were reinstalled and secured, completing the battery pack restoration before moving on to the next installation stage. I stripped the high-voltage cables, applied heat shrink, and used a hydraulic crimping tool to create secure connections, then routed the orange cables through the engine bay along a planned path and secured them neatly for safety and space optimization. The radiator fan uses a temperature relay 32 degrees Fahrenheit to 250 degrees Fahrenheit, set around 100 degrees Fahrenheit to activate only when hot. I rebuilt the 16-gauge connector with waterproof heat shrink terminals, cut a small hole in the shroud for the temperature probe, then tested and tuned it with 95 degrees Fahrenheit water for accurate operation. installed the bus bars to connect the battery modules, neatly routed the sensor and cell tap wiring, and test fitted everything before final installation. The bus bars aligned perfectly, the wiring was clean, and the battery pack was ready to be installed into the car. I converted the classic fuel cap into a hidden J1772 charging port cover, preserving the vintage look while integrating modern EV charging. I removed the plastic cover, reworked the edges, and widened the mounting area for proper clearance. The high-voltage charging cables were rewired, resized, heat-shrunk, and routed to the front compartment. I used a 3D printed mount with a custom-cut rubber gasket for alignment and waterproofing. Finally, the unit was installed, sealed with silicone, and tested for smooth flip-open operation, leaving a hidden but fully functional charging port. I start by applying gasket sealant to the motor controller cooling plate, then compressing it into shape and tightening the bolts. During the pressure test, the water force exceeds expectations and completely blows out the seal. I disassemble everything, clean the surface, heat the material, and reapply the gasket for a perfect seal on the second attempt. Next, I install the cooling system for the rear battery box, with fluid ports located at the bottom. Rubber gaskets are used for sealing, while the hose diameter is reduced to balance pressure between the battery pack and the motor controller. At the front chassis, I use 3D scan data to fabricate a custom-fit metal undertray. On this tray, I mount the coolant pump at the lowest position and secure the hose routing points. It also acts as a protective shield for the high-voltage components below, protecting them from dirt, water, and road debris. I install an overflow tank to stabilize coolant volume in the system, combined with a flow control valve to regulate flow rate. 90-degree fittings are used to handle tight hose bends and optimize routing in confined spaces. The system is completed with 8 stable circulating lines, 2 for the front battery pack, 2 for the rear battery pack, 2 for the motor controller, and 2 for the overflow tank. Coolant returns to the radiator, flows down to the pump assembly in the low under tray, passes through a distribution block that splits it into each cooling loop, and continues circulating through the system. The liquid cooling system is now complete and ready for the electrical wiring stage. I install the brake transducer, machine it, add waterproof and insulating protection, and secure it to the brake line in the engine bay. I then route low-voltage CAN bus wiring for the brake sensors. Finally, I fabricate a Z-shaped bracket to protect the high-voltage wiring harness under the vehicle. I install the high-voltage system with large cables and a central junction box containing the BMS, contactors, and fuses. Low-voltage wiring is labeled and fully checked. Motor phase cables are crimped and insulated in orange. The controller is connected via RS232-USB and covered with a 3D printed cap. I inspect the rear battery pack on a lift, remeasuring signal ports and high-voltage cable routing before installation. I then attach metal mounting brackets using a drill/driver to create fixed mounting points for the chassis. The pack is moved into the rear trunk on a dolly and aligned into position. I go underneath the vehicle to tighten large bolts, securing the assembly to the chassis. I remove the original fuel filler area to create space for cable routing and install rubber grommets to protect the cables from metal abrasion. I replace straight coolant fittings with 90-degree elbows to avoid suspension interference. All coolant lines and high-voltage cables are secured under the chassis, neatly separated for safe operation. I install an MSD and 3D printed cover to isolate HV, install bus bars to reach 89 volts, and connect the BMS and verify CAN bus at 120/60 ohms before routing signal wiring. On startup, the system fails with contactor and CAN loss due to a frozen BMS. A pinched sensor wire is found and repaired, improving insulation to 8 gigohms. However, a pre-charge fail remains due to internal leakage in the HV junction box, blocking the system and requiring inspection. I begin upgrading the signal wiring and checking the entire high-voltage system. At startup, nothing responds, so I continue disassembling components, replacing the contactor, updating software, and reconfiguring the system. Next, I fix chassis grounding, reconnect charging signals, and verify every connection so the charger can finally recognize the vehicle. After multiple tests, I uncover more HV wiring issues, replace the charging control board, and optimize the entire system. A moment of silence. Then the cooling fan spins up, charging current appears, and finally the automatic charging system runs successfully. I complete the cooling system by connecting the water pump, radiator, controller, and motor into a closed loop system, then fill coolant, bleed air, and check for leaks. Next, I reorganize the electrical system, finish installing the batteries, grille, lights, hood, and interior parts. Finally, the MG badge is installed back in place, completing the transformation into a fully electric classic car. And here it is, the result of hundreds of hours of fabrication, wiring, and testing. The fully electric MGA is finally on the road. From a classic car to a completely new electric drivetrain, everything was built step by step to turn what once seemed impossible into reality.